Okay, James, this is just for you because you missed Friday's lesson. I haven't had time to do a proper one on the smartboard, so I'm just doing a quick one at home for you on how solar cells work. Okay, so we've got our N-doped semiconductor, our N-doped silicon here with our excess of electrons, our free electrons. Remember, it's all electrically neutral. Over here, this is our P-doped section, and holes are the primary charge carriers, but remember it's neutral at the moment. The instant we manufacture it, the instant we bring the P and N together, these electrons are buzzing everywhere. Well, some are going to wander across to this region here and fall into a hole and get trapped. So this is generating our depletion zone. So on the N side, you can see we're now depleted of charge carriers because there's no free electrons, and on the P side, we're depleted of charge carriers because there's no free holes because these electrons have fallen into the hole. Okay, so that sets up an electric field. Because the electrons have moved across to the left, that makes the left side of the depletion zone negative, and it makes the right hand side of the depletion zone positive. So we have this electric field across the depletion zone, pushing any electrons that were free to move across to the right, but of course none are free to move because they've fallen into holes. Remember, they're buzzing around because of a bit of thermal energy, but not enough to sort of get them across that depletion zone. Okay, what we've got here with the yellow is we've got a wire connected to a load like a resistor or a motor or something like that from one side of our solar cell to the other side. Remember, because it's a wire, it's already full of electrons. The wires aren't empty tubes, they're already full of electrons. So there's our connecting wire. And along comes a little photon of light. Here comes a little photon of light, and it's going to hit somewhere in the depletion zone. It's going to hit somewhere in that lattice there. Now remember, that lattice looks something like this. Okay, it's a bunch of there's a lattice work of atoms, of silicon atoms with electrons everywhere. So there's still electrons everywhere, even where I haven't marked electrons and holes. They're part of the lattice. That photon of light is going to hit an electron and knock it free out of that lattice, with giving it some kinetic energy, because remember, that's the photoelectric effect, and now that photon of light is going to annihilate itself. Its energy is being given across to this pair, this hole and electron pair. Now normally they would probably just migrate back and fall back into each other, but because of this electric field, remember that's the size, the direction of the force on a positive charge, the holes are going to be migrating in this direction, and the electrons with lots of kinetic energy are going to be directed to move in this direction across that electric field, because remember, electrons have a force that's opposite of the direction of the electric field, so they're going to be pushed across into here. So we're going to find a whole lot of electrons with kinetic energy come banging into each other. Some are going to end up in that piece of wire there. This hole is going to migrate along away from there. These holes are all buzzing around, with thermal energy migrating away. Now this extra electron here is going to push that extra electron there is going to push his friend along, which is going to push his friend along and his friend along. In other words, we've generated an electromotive force. All of the electrons in the wire are going to push each other, along, never mind, you get the general idea, don't you? Push each other along the wire, and one at the other end is going to pop out and annihilate a hole. So what we just did then is a photon came in and created a whole electron pair. The electron goes this way, and then a whole electron pair is annihilated at this end here. So you see that hole and that electron no longer exist because that electron's fallen into the hole. So in a sense, that hole and electron pair has now disappeared. So we're back to the same net number of holes and free charge carriers that we had before, but we just pushed some electrons around a circuit. That's what happens. That's what a battery does. So anyway, along comes another little photon of light. It's going to hit. It has to hit the lattice somewhere in this depletion zone. Okay. It hits the electron in that lattice because of the photoelectric effect. The electron gets its kinetic energy from the photon, E equals hf, whole lot of kinetic energy. The electric field across the depletion zone pushes it this way, drags the hole, migrates that way also because of the electric field, and now we've got a whole lot of electrons all bunching up here on the wire. Well, that's going to make this end of the wire actually have a negative charge. So this end of the wire becomes negative, and this end of the wire becomes positive, because any electrons that wander this way, sort of wander into here, get munched up by a hole, and then the whole electron pair is basically annihilated. That electron is no longer a free electron. So now I've got a region here where I'm lacking electrons in the wire, a region here where I've got excess electrons. That makes this end negative and this end positive. And this is the field that actually pushes the electrons through the external circuit and through the load. So the electrons move this way, which of course would mean that conventional current would be traveling. So we'd say, for conventional current I, it's going to be traveling in that direction there in the Y, because the electrons are moving this way, because we've made this end negative and this end positive. So don't get confused between the electric fields. This electric field here is the electric field that's set up in the depletion zone. It's what gives the electrons their initial direction. So when we generate a whole electron pair, so here's a whole electron pair just sitting on the lattice, right? Along comes a photon, gives the electron kinetic energy. The electric field, it moves towards the positive, but remember it's got heaps of kinetic energy, so it just keeps going, bashing into all these other electrons, pushing more electrons into this wire here. The whole migrates this way. Every electron in the wire then sort of migrates, gets pushed around because they want to get away from other negatives and towards the positive. So they're all being kind of pushed around. Sorry about my load, they're not working very well. Getting pushed around in the wire, and that's going to force more electrons into here, and of course along comes one of these meandering holes and goes, oh yum, I like an electron, I'll eat that one up, and now we kind of annihilate the electron hole pair. Because the electron's not annihilated, it just goes back into the lattice as the normal sea of electrons that are here. We're only writing in the free electrons and the free holes. We're not drawing in all of the electrons and holes that are filled, because if they're filled, they're just part of the normal lattice, just like these guys here are filled and part of the normal lattice. I left them there so you can see why this side of the depletion zone is negatively charged. And that's how a solar cell, a photovoltaic, works. The N side is usually very thin and the P side is quite thick. The idea is that the light shines in through the N side, and on this side here, these wires, it's a grid of very fine wires, so that most of the photons can get past the solid pieces of metal and in through the N section into the depletion zone. It doesn't actually do anything good if a photon hits an electron here. It creates an electron hole pair here, but remember there's so many electrons around here, so here we go, we create a new whole electron pair that either the original electron or some other electron is just going to fall back into it, and so basically annihilate that. So that photon has achieved nothing at all in terms of generating our external current. It's only the photons that hit in the depletion zone that give rise to an EMF that's going to drive current through the external circuit, which is why solar cells aren't 100% efficient, because a lot of the photons end up interacting in the wrong part of the lattice. It's only the photons that interact with electrons in the depletion zone that give rise to that current. And I hope that helps you understand solar cells for Tuesday's assessment task.